I'm sure we all know that air pollution is a big problem, especially in urban areas. In fact, the World Health Organization states that poor air quality is associated with 7 million premature deaths annually. In order to tackle urban air quality, it's important to understand how pollutants disperse themselves through a city. But how do we actually model airflow? Well, numerical modelling, or CFD, which stands for Computational Fluid Dynamics, is a popular approach, especially as computing power increases. However, the turbulence models used have their limitations and are based on empirical data anyway. This experimental data comes from wind tunnel simulations, which also have the advantage over fieldwork campaigns in that conditions are fully controllable and repeatable. So, to model airflow through cities in a wind tunnel, a scale model is made and a pollutant source introduced to the setup. The concentration of this pollutant source can then be measured in any one location around the model at a time, but the apparatus for doing so is large, expensive, and complex to use. This is where my research comes in. My hypothesis is that pressure can be used as a proxy for concentration. Measuring pressure is much cheaper, simpler, and can be measured in multiple locations simultaneously. This would therefore simplify future experimental wind tunnel studies in pollutant dispersion. The basis of my hypothesis is that the transport equation tells us that the transport of pollutants is proportional to flow velocity, and Bernoulli's equation tells us that pressure is also proportional to flow velocity. It's therefore a logical conclusion that pressure and pollutant transport are linked. I just need to find the relationship between these two parameters. To do so, I've developed a model building called the Smart Cube, which has 500 pressure taps distributed over its surface. This model is placed in the wind tunnel with an upstream pollutant source, and for various source locations, I've measured the concentration at numerous locations around the cube, as well as simultaneously measuring the 500 pressure points over the whole surface of the cube. I've simulated the simplest case of just a cube in a tunnel, and a more realistic city landscape with an array of cubes, as shown in the images on the slide. Now, for both cases, I've identified a correlation between the concentration and the pressure, suggesting that a relationship between these two parameters does in fact exist. The next step of my research is to be able to infer information about concentration around the cube from pressure measurements, using the relationship between concentration in one location and pressure over the whole surface of the cube. This relationship will be valuable for simplifying future wind tunnel studies in pollutant dispersion, which help us understand how air flows around buildings through cities and therefore tackle urban air quality.